Hi, welcome to another lecture on linear algebra. Today we are going to talk about homogeneous linear systems. Let's go take a look at these particular equations. Sometimes it's called homogeneous, sometimes called homogeneous systems. The definition is very simple for these type of equation. If all of your right hand side are 0, so I have 4 examples here, right hand sides of all of them 0, these are called homogeneous systems. If you have anything other than 0 on the right hand side, we call them non-homogeneous, and the two of them are closely related to each other. Two issues. One is, well, why is this so significant? What are we going to do with it? And second, well, what's so special in terms of mathematics of it? What kind of solutions are we going to have? There is a solution of homogeneous systems that is very easy. When you look at this example, or this one, or this one, or this one, there is one solution that you can say right off the bat without doing any work at all, which is what? Well, since the right hand side is 0, if you make all of your variables equal to 0, that's going to be a solution. So if I say x and y, both of them are 0, well, of course, that would be a solution. Here, of course, x and y equal to 0, that makes a true statement. Here and here, same way. So that is referred to as a trivial solution. Trivial in mathematics, anything that you can get without doing any work. It's kind of clear from the outset. So trivial solution refers to a situation that you have x is equal to y equal to any other variables you got, and all of them are equal to 0. That is, of course, the case in all of these homogeneous systems. The question with them is that, is there anything else at all? Is there a non-trivial solution to be found? And toward the end of semester, we are going to come back to this, and it's going to be our major bread and butter. That, for example, if you look at this one, of course, we have non-trivial solutions. For example, if x is minus 3 and y is 2, that's of course a solution of this equation, and it's non-trivial. It's not one of these. Of course, you could have taken say 6 and minus 4, that would have been another one, and so on. Toward the end of the semester, we come across a very interesting problem. Suppose I erase this and then I replace it by some parameter. I say find k, so that I will have some non-trivial solution. How do you find? So here's a question. Find the parameter k. Find k so that the system will have non-trivial solutions. What do you think we should do here? So maybe go and think about that for a second, or maybe 2 seconds, and then we said at the very beginning of a semester that let's have one aim for the course, which is understanding vibrations. Well, this type of definition and questions comes up in the study of vibrations as well, in differential equations. You do them in your differential equation class, and also in your physics and engineering classes. So the study of non-homogeneous system corresponds to the situation where you have an external force acting on your system. Homogeneous systems is when there is no external force. And of course, to understand this, we need to understand that one first, and then combine them together. let me go ahead and just take a few minutes of your time, show you a little bit of an interesting experiment where we are headed in the semester, and hopefully by the end of semester we are going to have this issue resolved. So here we have forced oscillation resonance. What's happening is that we have this spring, a weight is attached to it, and if I didn't have anything else, if there was that weight by itself attached to the spring, the top spring here, I would have an example of a homogeneous system or homogeneous equation. If I attach an external force to my setup, here's an external force which is controlled by this mechanism here. There's going to be a pin that's going to be pushing up and down, pushing on this thing and making the whole thing to vibrate in an interesting fashion. So if there was none of these equipment down here, of course the item will go just up and down in a simple harmonic motion. But here we are going to see something else, the issue of resonance we had seen at the beginning of a semester. So let's go ahead and take a look at this for a few minutes. All you have to do is to tolerate a British accent for 4 minutes and see something quite interesting. Let's see.
Time for some physics fun. What I've got set up here is a vibration generator. So the pin here will move up and down. I have a spring, and that's a spring with a K of about 30, and then I have a 100-gram mass, and I have a second spring attached to a clamp stand that's out of shot. So it's a dead simple experiment to do. We have the signal generator at the back here, and at the moment I've turned down the amplitude. So I'm going to turn up the amplitude, which is hidden, and we're going to put it on maximum, and hopefully you can clearly see that this pin now is vibrating at a frequency of 2.06 Hertz. Now let's see what happens if we dial down the frequency. We're now going at 1 Hertz, well, nearly a Hertz there, 1 Hertz frequency. So up and down. Okay, let's go up a little bit. We'll go slowly so you can clearly see, getting a bit more motion with that mass. And I've done a scale on the back here, and this is in centimetres, so it's every 2 centimetres. I did a bit of a line at the mid value. Now it's not perfect because I'm on a bit of an angle, but it's not really designed to do an accurate display. We're just looking for an overall effect. So 2 Hertz, pretty much the same thing is happening. So let's go up a little bit more. There we go. 2.5. It seems to have died off now. There's not a lot happening. 2.7, 2.8, 3 Hertz. Interesting. Wow. 3.2, 3.3. Crikey. The amplitude is massive. Looking at least 14 centimetres.
So one thing we'll learn there is the meaning of the word crikey, I guess. In addition, we learn about resonance. You notice that at a particular frequency that object starts to vibrate rather wildly. That's what we see. He goes up and then the amplitude dies down. So there is a magical number there.
It's died off.
The resonance frequency that makes this thing to oscillate wild. So here's our external force.
It's gone. Let's go back.
It's external force that is controlling the system, but of course the internal property of the system is important. So that external pin there is like the numbers that we have on this right hand side, and the rest of the setup is our homogeneous system, and we are trying to kind of match them against each other so that we get the maximum resonance. Right now, simple mathematics. What should be the number k so that the system will have non-trivial solutions? Well, we learned from previous cases, maybe even way back in college algebra in high school. 2x plus 3y is a certain line, is that right? So 2x plus 3y, if you want to write it in the style that you write in high school, you write it as y is equal to minus 2/3 of x, is that right? Minus 2/3 of x. How about the other one? The other one is y is equal to minus 5 over k of x. So y minus 2/3 of x, some line that goes here. This one, well, if it is a different slope, then they all meet each other just at 0, and all you get is trivial solution. If you want non-trivial solution, what should you do? For the non-trivial solution, that blue has to move here right on top of the first one, so that you'll have infinitely many solutions. Which means what? Which means that the two slopes have to be the same. Minus 2/3 has to be equal to minus 5 over k, which means 2k has to be equal to 3 times 5, or 2k minus 3 times 5 has to be equal to 0. So how do we come to this equation quickly? Well, we are going to see this thing again later on in the semester. It's the concept of determinant. If I multiply these two, 2k, and multiply the other two and subtract them from each other, that is the concept of determinant. If my determinant is 0, my system is going to have non-trivial solution. To make it simple, this equation has to be a multiple of that equation. If this is 2.5 times bigger than that, then k has to be 2.5 times bigger than that. So k becomes 2.5 times 3, that becomes 7.5. Of course, if you solve this equation also, you get 7.5. So finding a parameter that makes your homogeneous system to have non-trivial solution is going to be something that's going to be playing a significant role for us later on. It has something to do with the frequency of that vibration that you looked at, and you can do some of the problems in that simple way. Of course, for 2 by 2, again, the recipe very simple. The product of these two has to be equal to the product of those two, or in other words, they have to be proportional to have non-trivial solution. How about these bigger systems? How do you handle that? Well, again, we learned we have a software that's going to help us not to spend so much time on the pain of the arithmetic here. So I can just go ahead and plug it into my software and check to see, okay, what is it that we are going to check? We are going to check to see if there is any free parameters. Then I'll have non-trivial solutions. If not, then it's going to be all trivial. So let's just go ahead and do this one quickly. Let's go back to our favorite software here. It was a 3 by 3, so I will go reset this thing so it goes back to where it was, and then edit 3 by 3. I don't need to change that. This one was 1 2 3 4 6 11. So some numbers, just random numbers, so we don't expect our numbers to look pretty anymore, but thankfully we have a calculator here that takes the pain away. So it's not going to be what we saw with what Bart was saying. We have to keep Bart always happy. This is not boring and pointless. It is actually something meaningful. So let's see. We want to solve this thing. Right hand side is 0. If you want to write it, that's okay. If you don't write it, that's also okay. With zeros, however you combine them, you always have zeros there, so there's nothing to change. So what do we do here? So resume, take this and eliminate that, take this thing and normalize it. So I divide it by -2, take this and eliminate that, and you notice the last one did not become 0. If you want to normalize that 2, let's divide it by itself. So what does this mean? I have x and a y and a z, and right hand side is 0. So if you do back substitution, here your z is equal to 0, you go back here and your y is equal to 0, you go back here and your x also becomes 0. So the solution of this system, we found quickly that the solution of this one was simply x and y and z, they're all just 0, and there was no non-trivial solution. There is a situation where we know that there will be a non-trivial solution before we even try it. So the fact that there is non-trivial solution itself is going to become a bit of a trivial thing, and that is when you have fewer equations than you have variables. So if you have fewer equations, let's write this better. Number of equations is less than number of variables, like this case. Number of equation is less than number of variables. In that case, we always will have non-trivial solutions. That is, we have solutions other than just all zeros. All zeros obviously matches. Does anything else work? Now let me see from the stuff we talked about in the very first chapter. What is it about this equation from point of view of geometry that you can immediately see that you are going to have infinitely many solutions here? What is it about it? You remember we talked about lines and planes and such. What is this an equation of? 2x plus 3y plus z equal to 0, huh? That was equation of a, what did you say? Equation of a plane. This is the equation of another plane. Having as a system, it means we are looking at the intersection of those two planes. Now if you have two planes and both of the planes pass through origin, so they do have a common point. So if two planes have a common point, could it be that they'll have just one point in common? Or is it that they will have infinitely many points in common? Of course, two points that have a point in common, either they have an entire line in common, or the two planes are entirely coinciding on top of each other. It's just a single plane. So you remember we talked about finding the intersection of two planes. So some of the question in this section come back to the same topic that we had before. So if you want to do this thing by hand, you are free to do it like this. So I have 2, 3, 1, 4, 7, 3. So remember, this was for x, this is for y, this is for z. If you for homogeneous equation, again we said it's optional if you want to carry the right hand side or not, because it's all 0 and it never changes. If you want to put it there, put it there. If you don't want to put it, that's fine. So this is if you want to have right hand side. However you combine them, they always stay 0. So if you want to save a little bit on writing, you can just ignore writing it. Well, what do we do here? We said, well, minus twice row 1 added to row 2 that is designed to get rid of this entry. So what do I get now? 2, 3, 1, of course 0. This becomes 0 and this becomes 1 and this is also 1. And well, as we said, this thing never changes, always 0. So if you want to do by back substitution, what does this thing read like? 2x plus 3y plus 1z is equal to 0. Second equation reads like what? Y plus z is equal to 0. What did we do to handle this? We said, okay, let's z to be our free parameter. And customary thing was to call it by some other letter like t. Start from the last. You see, y becomes minus t. So if this is minus, then for the first equation we have 2x is equal to minus 3y minus z. So this becomes minus 3 times minus t minus t. So that becomes 3t minus t. That becomes 2t. And luckily we get our x, a clean expression. X is just t. Then we wrote that as x, y, z is equal to t times 1 minus 1, 1. What did this mean? It means that if this is some plane number 1, and then another plane number 2, their intersection is going to be a line. They have a point in common. It has to be either a line or a plane. In this case, the intersection is a plane. Excuse me, the intersection is a line. And this is the direction vector of the line. So general story in this section is that if the number of equations is less than the number of variables, then we'll have non-trivial solutions, which means we are going to have infinitely many solutions. Infinitely many non-trivial solutions. So an example of that was intersection of two planes that go through the origin. Okay, simple short topic here. We are going to move on to the next section, and we are going to have a little bit of a theoretical discussion in section 2.3. You are going to see the word span is being used a lot, and linear independence and dependence is going to be talked about in section 2.3 if you want to read it ahead. Okay, good luck and God bless until the next meeting.